Okay, now let's talk about section 13.5, the binomial theorem. Okay, so what is the binomial theorem? Let's start from some computation. We already know what is so-called complete square formula. So x plus a squared is equal to x squared plus 2xa plus a squared. Well, this is a well-known formula. We know them from high school. And if we increase the power, x plus a cubed, possibly not everyone still remember it, but if you just do the computation, term by term multiplication, expand this, you will see that it is x cubed plus 3 x squared a plus 3 xa squared plus a cubed. All right, and if you continue this process, we have x plus a to fourth power. Or possibly you just did some exercise like this, but you never consider it as a formula. You do the long expansion, and possibly after 1 or 2 minutes, you simplify and combine like terms. You will have x to fourth power plus 4x cubed a plus 6 x squared a squared plus 4x a cubed plus a to fourth power. Let me check if I'm right or not. Yeah, that's right. All right, so of course we can continue this. If we continue this, it's not interesting because we really have to expand it without any additional support. Just expand it, take time. It's just a matter of time. But now let's study this or observe this pattern. You will see that here is square. This is x squared, cubed, x cubed, fourth power, x to fourth power. So if I have x plus a to nth power, I believe it must start from x to nth power. It must start from x to nth power. And it's always addition, so we always have addition. Then what's next term? Next term, you see, x to fourth power, x cubed. The degree it becomes the next integer, smaller integer. Here, x cubed, x squared. So the next term must contain x to the power of n minus 1. You just subtract 1 from n. And also you see here, together with a copy of a. What coefficient? The coefficient changes. Coefficient changes. You see 2, 3, 4. Of course, you may guess, okay, here's 2, here's 2, here 3, here 3, here's 4, here's 4. Then possibly here's 5. N, right? If this is n, this will be n. But let's leave it here. Assume we don't know it. And next, you continue the decreasing process. Here's a 4, 3, 2, here's 1, right? And nothing. So the power of x term, the x factor decreases, and the power of a factor increases. So here there's no a. 1, 2, 3, 4. So this is supposed to be a squared. And again, now this time it's not that clear, right? Here you can say, okay, we have 2, 3, 4 as is 2, 3, 4, but this part is not that clear. So we do need a formula. So I leave it here. It's always addition, and next term, if you want to write, it's going to be x to the power n minus 3, a to the power n cubed, and until you add a to nth power. You see, a squared, a cubed, a to fourth power, and here a to nth power, and comes from this original. So in this expansion, we know almost everything except the coefficient. We don't know the coefficient, right? We have no idea about the coefficient. 1n is extremely big. So the binomial theorem will tell us what are the coefficients of those terms. All right, so that's how binomial theorem works. The binomial theorem will tell us all these coefficients. Once we know the coefficients, we get the complete expansion, right? So what are those coefficients? Let's first introduce a notation. We say evaluate the symbol and choose j. So this one we call it, this big parenthesis, top n bottom j. It's not a fraction. It's not a fraction. It's just a special symbol. Reads n taken j. Well, this n taken j at a time, or n choose j, or n choose j. You can also say n choose j. I prefer this one. It's a simpler. Okay, so we may not have enough time to discuss the origin of this. We will just have the simple example. For example, we have 1, 2, 3, 4. We have 4 balls with numbers. Okay, the first ball has number 1, the second ball has number 2. And we want to take, now let's just say 2 balls randomly. For example, I can take ball number 1 and number 2, or maybe I take a ball number 1 and number 3. So the question is, how many different way can we have? How many different combination can we have, right? So for example, let's list them. Those numbers are not small, are not big. So let's list all the possibilities. So we may choose ball 1 and ball 2. This is one case. Or we choose ball 1 and ball 3. Another case. We just randomly take them. There's no order. Or we may choose ball 1 and ball 4. Case. 3 cases. 3 cases when your selection has a ball 1. Or there's no other option. Now let's see. We may choose ball 2 and ball 3. Or ball 2 with ball 4. Or ball 3 with ball 4. You can check that there is no other way to select 2 balls randomly from 4 balls with numbers. Okay, so there are 6 different ways for us to have those 2 balls. Okay, this number 6, we denote it as 4. From 4 balls, we choose 2. 4 choose 2. From 4 balls, we choose 2. This is number 6. So that's the origin, the combinatorics number from the practice. How do we understand it? And of course, if I have a large number, we cannot just evaluate this expression by listing all the possibilities. That's impossible, right? So that's just a simple example which shows us what is the original meaning of this symbol. This symbol just means you have n balls, you are going to choose j balls from those n balls and choose j. That's all. And taken j at a time. All right. So what is the formula to evaluate this and choose j? Let's here they directly say the definition, or you can say it theorem. The definition: if j and n are integers, with j greater than or equal to 0, less than or equal to n. Okay, j can be n, j can be 0, but j cannot be bigger than it. J has to be positive. Then the symbol n choose j is defined by n choose j is equal to n factorial over j factorial times n minus j factorial. So first of all, this is a complete definition. So this is a definition. Let's explain it. N factorial, this symbol means number 1 times number 2 times number 3 up to number n. So n factorial means the product of the first n integers, natural numbers, n natural numbers. The product of the first n natural numbers. For example, if you have 2 factorial, it means 1 times 2 is 2. And 1 factorial, we define it to be 1. You just get one number. You do not have product. It's just 1. And if you have a 3 factorial, it's a 1 times 2 times a 3. Well, it's a 6. There's no simple way or quick way to compute. You just really do the product. If you can do more. 4 factorial is 1 times 2 times a 3 times a 4. So see here, 2 times 3 is 6. 6 times 4 is 24. And 5 factorial is 1 times 2 times a 3 times a 4 times a 5. We just compute 1 times 2 times 3 times 4 times 5. This whole thing is 24, right? From here. 24 times 5 is 120. And the 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. You do really have to do the computation. And the product from 1 to 5, we know it's 120 times 6 is 720. This number grows very fast, but it's just this product. No simple way, no shortcut to compute. All right, so this is a factorial. And in this whole process, there's a special setting, 0 factorial, because j can be 0. 0 factorial, we define it to be 1. This is a special definition. 0 factorial does not follow this definition. 0 factorial is just 1. It's not 0. It's not 0. Okay? So now let's check this. N choose 2. N choose 2. So the factorial means, so here's n. The numerator is 4 factorial. Denominator, j factorial. J is this 2 factorial. N minus j. So you see here, you first do the subtraction. 4 minus 2 is 2. And then you do factorial. Well, let's check. 4 factorial is 1 times 2 times 3 times 4. 2 factorial, we know it's number 2. And second 2 factorial, we know it's number 2. So this is 2 factorial, number 2. 2 factorial, number 2. 2 times 2 is 4. Cancelled with this 4. So 1 times 2 times 3 is equal to 6. This is exactly what we observed by listing our possibilities. Right? See it? So this is the definition or the formula for the evaluation of n choose j. N choose j. Let's do more examples. So A, let's see, 3 choose 1. 3 choose 1 by definition is 3 factorial over 1 factorial over 3 minus 1 factorial. So 3 factorial numerator, 1 factorial, and the difference 3 minus 1, 2 factorial. 3 factorial, we know it's a 6. 1 factorial is a 1. It's a product, so the product with 1 you don't need to write. 2 factorial is 2. So this symbol is equal to 3. You will see that this symbol is always an integer. If you get some fractions, it means you're wrong. Part B is this 4, 2. We just did it. Part C. Part C is 8 choose 7. 8 choose 7 is 8 factorial over 7 factorial. 8 minus 7 is 1 factorial. In the factorial, in the n choose j operation, it's easier if you can cancel many terms. For example, here 8 factorial. What is 8 factorial? Of course, we will not compute precisely. We will not say, okay, 6 factorial is 720. If you check 8 factorial, it will be even bigger. That's not useful. So when you try to evaluate this symbol, you always just write them as a product, because with a product we can cancel terms. 7 factorial, 1 times 2 times 3 times 4 times 5, 6, and 7. 1 factorial is 1, you don't have to write. Remember, they are all product you can cancel. You see here 1 2 3 4 5 7 cancel, 1 2 3 4 5 7 cancel. So you cancel most of the term. You only have 8 in the numerator, so this denominator is 1. So this C is equal to 8. Very fast. Don't do the multiplication, do the cancellation first. Do the cancellation first. Right? Okay. Another thing, in the textbook, it has a symbol calculator, which is not allowed in the exam. So if you really have a big number, 65 choose 15, of course there's no 65 minus 15 is 50 factorial. There's no simple way. There's really no simple way. So you see here 65 is 1 times 2 times, okay, let's write 50 and 51, 52, 53 after up to 65. This is product. And here 15 is 1 times 2 up to 15. 50 factorial is 1 times 2 times up to 50. That's the reason I write 50 here. So you cancel 1 up to 50, cancel 1 up to 50, but you still have the numerator. Start from here. Start from 51 times 52 times 65. The denominator is 1 times 2 times 3 times 15. So this number, trust me, you will not try to evaluate. It's really a calculator job, but we will not allow calculator in the exam. So it means you will not see a huge number in the exam computation. All right. So in the textbook, they give an estimation. The estimation is like 2.1 times 10 to power 14. So you have 14 zeros. It's big. 60 is a million. Okay? 60 is a million. 90 is a billion. Here is a 14 zero. There are 14 zeros. 10 to 14 means here there are 14 zeros. 10 to 6 is a million. 10 to 9 is a billion. It's a huge number. So this number is a very large. Okay, this can only be done by calculator. You will not do it by hand. All right, so that's the definition of n choose j. And in the n choose j symbol, we have some commonly used value. We will memorize them. First, you see, j is between 0 and n. Let's take some special number, 0. If j is 0, it's n factorial, 0 factorial, n minus 0 is also n factorial. 0 factorial is 1. Remember that we say 0 factorial is 1. N factorial over n factorial is 1, so this is always 1. N choose 0 is always 1. How do we understand it? N choose 0 is always 1. So you have 4 balls, you choose nothing. There's only one case. You choose nothing. So there's only one possibility. The other one, n choose 1. N choose 1 is n factorial, 1 factorial, n minus 1 factorial. This one you can check here. Not that. This one is similar. So 8 is n factorial, 1 factorial. 7 is n minus 1 factorial. So basically, you cancel most of the term. You only have n survives. Only have n survives. This one is similar to this. Check this example C. You will see that from 1 to 7, all the factors are cancelled. From 1 to n minus 1, all the factors cancelled. There's only n left. And n choose n minus 1. So this one also easy to understand. You have 4 balls. Every time you just choose one. You can choose first one, you can choose second one, third one, or fourth one. Just 4 cases. So n choose 1 is equal to n. Okay, n choose n minus 1. N factorial over n minus 1 factorial. N minus 1 is 1 factorial. You see these two symbols are same. It is also equal to n. This one is also easy to understand. If you have 4 balls, you choose 3 of them. Now this time you do not consider 3. You consider what is not selected. You choose 1 to 3, you leave 4. You choose 1 to 4, you leave 3. You choose 1, 3, 4, you leave ball 2. You choose 2, 3, 4, you leave ball 1. So every time you will leave 1 ball out of a selection. So there are only 4 ways. So that's n. Right? N choose n minus 1 is equal to n. N choose 1 is also equal to n. And the other one is n choose n. You have 4 balls, you choose 4 balls, 1 way. You have 4 balls, you choose 4 balls, there's only 1 way to select them. You just take all of them. So those 4 values are commonly used. You will use them almost all the times. All right, so those are 4 commonly used computation. Well, still it's too difficult to evaluate. Now let's develop a quick formula. Quick in certain sense is not extremely quick. So let me leave it here for a second. Okay, now let's go back to the original one, this one. This was our starting point. Starting point, remember that we have x plus, here I didn't write x plus a to first power. If I write x plus a to first power, it's just x plus a, right? You do not have power. So x plus a, and x plus a to 0's power is 1. X plus a to 0's power, this is to first power, to 0's power is equal to 1. So we start from this 1. Then x plus a to first power, you have x, you have a. I do not copy the term x and a, because x and a, we already know the pattern. What we don't know are the coefficient. So I'm going to record the coefficient. So x has coefficient of 1, a has coefficient of 1. So I write 1, 1 like this. And next, we observe x plus a squared, the next layer. This is x plus a to 0th power. This is x plus a to 1st power. X plus a squared, the coefficient is 1, 2, 1. So we get 1, 2, 1. This is x plus a squared. And then we check this x plus a cubed. 1, 3, 3, 1. We only check the coefficient. 1, 3, 3, 1. It's like the layers of cakes. And then you have a 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Remember, this is not a crazy formula. It's just expansion by computation. No tricks at all. No tricks at all. You just do x plus a squared and times x plus a, you get x plus a cubed, and then times x plus a, you get x plus a to 4th power. And you simplify it like this. Okay, now let's observe what we have. This triangle, we consider as a triangle. This triangle, the left side, the right side are always 1. They're always 1. And then the interesting property is that you add these two. This is a vertical triangle, opposite triangle. You add 1 to 1, you get 2. And you add 1 to 2, you get 3. You see, 2 and 1, you get 3. You add 1 and 3, you get 4. You get you add 3 and 3, you get 7. You add 3 and 1, you get 4. If we have this observation, let's predict the next layer, x plus a to 5th power. So remember, we said two sides are always 1. So these two numbers, you don't need to worry. And then you have 1 add 4, you will get 5 at this place. 4 and 6, you're going to have 10 at this place. 6 and 4, you're going to have 10 at this place. 4 and 1, you add 4 and 1, you get 5 at this place. All right? So what does this mean? This means if we expand x plus a to 5th power, the coefficients should be them. Well, I'm going to write it down. X plus a to 5th power is x to 5th power. This is 1. 1 is always a coefficient of x to 5th power. 5x to 4th power a plus 10x cubed a squared. How do I know that? You see, 5, 4, 3. So the degree of x is decreasing 1 by 1. The degree of a is increasing 1 by 1. And 10x squared a cubed, 5x a to 4th power and a to 5th power. This is exactly the case. You expand it. You really do the expansion, you will have this. This is correct. This is correct. All right? So if we expand it by hand, little by little, we will eventually have this formula. But with this triangle, we can quickly write down the formula because we already know the pattern, and by the formula, by this triangle, we can predict the coefficient 1, 5, 10, 10, 5, 1. You see, 1, 5, 10, 10, 5, 1. All right? So that's a very quick way. But if you want to get x plus a to 65th power, you have to get the complete triangle. I say it's a quick way, but quick in certain sense. You must get the complete triangle in order to get the next one. You cannot skip any step. And this triangle is called the Pascal's triangle. This is called Pascal triangle. You can continue this. You can continue. For example, let's continue one more. Even though it's not useful, but let's continue. So it's 1. It's always 1, 1. And 1 plus 5, 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5 is 15. 5 plus 1 is 6. So those numbers are the coefficient of x plus a to 6 power, term by term coefficients. All right. So this is a Pascal's triangle. Pascal's triangle. It's very useful. And okay, now let's state the binomial theorem. The binomial theorem. The binomial theorem is that x plus a to nth power is n choose 0 x to nth power plus n choose 1 x to the power n minus 1 a n choose 2 x to the power n minus 2 a squared and up to n choose n minus 1 x a to power n plus 1 and n choose n a to nth power. So actually those n choose j are exactly the coefficient of each corresponding term. N choose j are exactly the coefficient of each corresponding term. Right? So this is so-called the binomial theorem. Binomial theorem. So here 0 means there's no a. This is 0. The bottom line, the bottom point, are the bottom numbers are the powers of a. Here there's no a. Here's a 1a, 2 a's, n minus 1 a's, or n a's. Okay. And because of this n choose j is also called the binomial coefficient. It's called a binomial coefficient. All right, so that's a theorem. We're not going to prove it. Prove it will take a few minutes, some time to show it. We need some understanding about the expansion one by one. And now let's just see how to apply this theorem, this formula. We want to expand x plus 2 to fifth power. Of course, remember that even though we have those symbols as coefficient, if you really want to get the concrete numbers, those numbers cannot be very big. If you have 65, first of all, you will have 66 terms. You see, it starts from 0, 0, 1, 2, 3, up to n. So there are how many terms? N plus 1 terms. There are n plus 1 terms, not n terms. Check here. You have squared 3 terms, cubed 4 terms, fourth power 5 terms. Okay, you always have n plus 1 terms. If you have power 65, you have 66 terms. And for each one, you have to compute 66 n choose j. That's not an easy job. Even the 65 choose 15, you will get such a huge number. So you will never try it by hand. We can possibly only do those simple ones. Okay, let's try to expand it. By the binomial theorem, n choose 0, x to 5, n choose 1, x to 4, a is 2, n choose 2, 5, n is a 5. There's no n. N is a 5. N is a 5. X cubed, 2 squared, 5 choose 3, x squared 2 cubed. 5 choose 4, x 2 to 4th power, and 5 choose 5, 2 to 5th power. Okay, now let's simplify it. 5 choose 0. Remember that n choose 0 is always 1, so this term is coefficient is 1, so it's x to 5th power. We know that the leading term is always has coefficient 1. 5 choose 1, 5 choose 1, n choose 1 is always n, so this is 5 times 2 is 10. 5 choose 2, this one we really need to compute. 5 choose 2 is 5 factorial over 2 factorial. 2 minus 5 is a 3 factorial. So it's a 1, 2, 3, 4, 5. 2 factorial is 2. 3 factorial, 1 times 2 times 3. So let's cancel 2, 3, cancel 2, 3. 4 times 5 is 20 over 2 is 10. So this is 10. 10 times 2 squared is 4. 40 x cubed. 5 choose 3 is 5 factorial, 3 factorial over 2 factorial. You see, this is a 5 factorial over 2 factorial, 3 factorial. Here's a 5 factorial over 3 factorial, 2 factorial. They're equal actually. This is also 10. So 10. 2 cubed is 8. 8 times 10, 80. 5 choose 4. 5 choose 4 comes from n choose n minus 1. N minus 1 is n, so this is a 5. 2 to 4th power. 2 to 4th power is a 16. This is 16. 16 times 5 is, this is 8. 16 times 5 is 80 also. 80x. 5 choose 5 is 1. 2 to 5th power is 32. So you see here, even you have a small number, small power is still very complex. It's not that easy. Right? So you see, same thing. You check here. You have a 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. That's exactly the coefficient, binomial coefficients. Okay, see what I say? So 5 choose 0, 1. 5 choose 1, 5. 5 choose 2, 10. 5 choose 3, 10. 5 choose 4, 5. 5 choose 5, 1. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Those numbers are not because you also multiply by 2, 2 cubed, 2 squared, 2 cubed, 2 4, 2 5. You have different number because you also multiply by the powers of a to certain power. See it? This expansion, you have to do it carefully because it's really easy to make mistake. It's easy to make mistakes. Okay, next, let's see more examples. The binomial theorem can only be applied to x plus a to certain power. If we have 2y minus 3 to 4th power, we also want to apply the binomial theorem. How do we do that? First, you have to really consider it as x plus a. So you have 2y plus negative 3 to 4th power. This is your x. This is your a. And in the middle is addition. It must be addition. Okay, once you have them, you get 4 choose 0, 2y, the whole thing to 4th power. 4 choose 1, 2y cubed, a, negative 3, first power. 4 choose 2, 2y squared, negative 3 squared. 4 choose 3, 2y, and negative 3 cubed, and plus 4 choose 4, negative 3 to fourth power, negative 3 to fourth power. Okay, you see 0, 1, 2, 3, 4, 5 terms. And then you check here, it's a 1. 4 choose 0 is a 1. 4 choose 1 is a 4. 4 choose 2, we computed. We used it as an example, it's a 6. 4 choose 3 is a 4. 4 choose 4 is a 1. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. They are the binomial coefficients. If it's small, you can just use that Pascal's triangle to quickly determine those special symbols. Okay, 1 you don't copy. Then this is 2y to fourth power. It's 2 to fourth power, 16. Y to fourth power, y to fourth power. All right, and this one, this is 8y cubed. So you get 4 times 8y cubed, 32y cubed. 32y cubed times negative 3. It becomes minus 96y cubed. Okay, so 4 times 8, 32. 32 times 3, 96, negative, so it's minus y cubed. Here, it's a 6. A 2y squared is a 4y squared. 6 times 4, 24, right? 24y squared. Negative 3 squared is 9 times 9. 24 times 9, what is it? So 24 times 9, 36. 2 times 9, 18. 18 plus 3 is 21. So it's 216 y squared. All right, so I use 6 times 4, I get a 24y squared. Negative 3 squared is 9. 9 times it is a product. I'm trying to simplify it. 24 times 9 is 216y squared. And here this one, it's a 4 times 2y is 8y. Negative 3 cubed is negative 27. 8 negative 27. It's a 56. It's 16. 261. Right? But this is a minus. That's negative. So minus 216. 216y. And final one. Negative 3 to fourth power is 81. Positive 81. So that's it. Just be careful. Compute each term carefully. Compute each term carefully. It's very easy to make silly mistake. All right? It's very easy to make the silly mistake. Okay, so those two examples. First example is very standard. You have x plus a to certain power. And second example, you have to identify x and a for different term and then simplify it. Just be careful. And they have smaller power, 5, 4, they are smaller. If you have a large power, possibly you don't need to get the whole sequence, whole list. You just need to find the coefficient of y to 8th power in the expansion. Of 2y plus 3 to 10th power. Okay, so we don't want to expand the whole thing. Whole thing is too long. There are 11 terms. We don't want to expand it. We just want the coefficient of y to 8th power. What is the strategy to do it? You see, first 10 choose 0. This is a x. This is a. So it's a 2y to 10th power. And 10 choose 1. 2y to 9th power times 3. 10 choose 2. 2y to 8th power times 3 squared. 10 choose 2. To choose 3. 2y to 7th power, 3 cubed. and so on. After you write those terms, you will realize here you will have y to 10th power. This term you will have y to 9th power, and this term you will have y to 8th power. You see, we need y to 8th power, so we will only compute or simplify this term. This term you will have y to 7th power, but that's not what we are interested. So we only check this term. 10 choose 2. 2y to 8th power times 3 squared. Be careful. Be careful. It's very annoying when you write it. Okay, now let's try it. 10 choose 2. 10 factorial over 2 factorial over 10 minus 2, 8. 8 factorial. 2y to 8th power is 2 to 8th power, y to 8th power. 3 squared is 9. Right? Let's check it. So 10 factorial is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 to 8. 2 to 8. Here is the numerator. You see? This is always numerator. 2 to 8. And 9. And y to 8th power. This is numerator. Denominator. 2 factorial is 2. 8 factorial. 1, 2, 3, 4, 5, 6, 7, 8. Be careful. In this computation, you almost cancel most of the terms. The product from 1 to 8. The product from 1 to 8. This number 2, you cancel one copy. This becomes 7. Okay, what we have? It is 9 times 10 times 2 to 7 times 9 and y cubed. Y to 8th power. Y to 8th power. Denominator, all the numbers are cancelled, so denominator is 1. So now you really have to compute. 9 times 9, 81. Times 10, 810. 2 to 7, what is 2 to 7? 2 to 7 is, well, 2 times 2 times 2 times 2 times 2 times 1, 2, 3, 4, 5, 6, 7. 4, 8, 16, 32, 64, 128. 128. 2 to 7 is 128, right? 2 times 2 is 4, times 2, 8, times 2, 16, times 2, 32, times 2, 64, times 2, 128. And then 128 times 81. 8 times 8, 64, 6. 2 times 8, 16, plus 6, 200, no, 22. 2 times 8, 16, plus 6. Remember, 8 times 8 is 64, plus 6 is 22. 22 moved to 1 times 8 is 8, plus 2 is 10. So it's equal to 103680 y to 8th power. Right? Am I right? Yeah, I'm right. So the coefficient, the answer, the coefficient is this huge number. Just be careful. Don't make mistake. Okay, don't make a mistake. Good. Excellent. So let's see another example. We just try to practice this formula and let you memorize it and see how we can ask the question. Find the sixth term in the expansion of x plus 2 to 9th power. X plus 2 to 9th power, there are 10 terms. And be careful, when we write down the binomial theorem, we have certain order that will help us to completely write everything. What is order? It's always 9 choose 0, blah, blah, and plus 9 choose 1 with a term, and 9 choose 2 with a term, and 9 choose 3 with a term. You will see 9 choose 0 is first term, 9 choose 1 is second term, 9 choose 2 third term, 9 choose 3 is fourth term. So if we want to get 9 choose 6, is actually not if we want to get the sixth term, we actually have 9 choose 5. 9 choose 5, the first term is going to be 5 minus 4. N choose j, if you compute it, it's n minus j, a to j's power. You see, remember that we said that j is always the power of a. What is the power of x? J increase 1, a increase power by 1, then x will decrease power by 1. So a has power j, x will have power n minus j. So x has power 9 minus 5 is 4. A is this 2. 2 has power 5. So this is the sixth term. This is the sixth term. This is the j plus 1's term. N choose j, then this is a j plus 1's term. Okay, then let's check. And 9 choose 5, x to 4, 2 to 5. It's also a very long computation. It's a 9 factorial, 5 factorial, 4 factorial, x to 4. 2 to 5 is 32. Just do the computation, you will get it. It is equal to 32. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 factorial, 1, 2, 3, 4, 5. 4 factorial, 1, 2, 3, 4. X to 4 and 13, 2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 cancelled. 2 times 3 is 6. 4 cancelled with 8, you get 2. So the numerator is 6 times 2 times 9 times 32 times x to 4th power. All right, so there's no way we have to compute it. So it's 14 times 9 is 126. 126 is 2 times 7 is 14. 14 times 9 is 126. 126 times 32. This is 12, 5, and 2. This is 18, 7, and 3, 5, 2, 3, 0, 4. It's equal to 4,032 x to 4th power. 4,032 x to 4th power. Good. Okay. So that's the thing we can ask, or we may ask about the binomial expansion, binomial theorem. And in the next part, there is a theorem. What is this theorem? This theorem is just abstract statement about this triangle. It claims two terms in the layer 4, add two adjacent terms in the layer 4. The sum is the term in the next layer. So the theorem is like this: n choose j minus 1 plus n choose j is equal to n plus 1 choose j. So you see, this term, that's the n choose j minus 1. This term is n choose j. You add them together, it's going to be next level. Next level comes from n plus 1. n plus 1 choose j. So that's this a theorem. It's just tell you why this is correct. It's not just observation. It has a solid proof, and this proof totally depend on the definition. N choose j is equal to n factorial over j factorial n minus j factorial. It's not interesting, so I'm going to skip it. Okay, so this is the complete material of the section 13.5. Okay, you're supposed to do the exercise to handle the binomial theorem. It's very useful, and be careful about your computation. All right, thank you very much. Let me show you what we just discussed. We have this. And second page. Third page. Fourth page. And the last page. Excellent. Thank you. I've finished.